So today, let's talk about how two, frankly, groundbreaking technologies are coming together to solve one of the biggest headaches in AI. And that is, how do you train incredibly powerful AI models on super sensitive data while making absolutely certain that data stays private? This isn't just some theory for a research paper. This is the new strategic playbook for building AI that people can actually trust. So let's just jump right in with a puzzle. It's a puzzle that leaders in finance, in healthcare, pretty much any regulated industry have to deal with every single day. Look, to build the kind of game-changing AI that can spot complex fraud or diagnose a rare disease, you need a ton of data. But, and it's a big but, strict rules like GDPR and HIPAA mean you are legally forbidden from just sharing that data around. So how in the world can you train an AI model on data you're not even allowed to see? Sounds impossible, right? Well, stick with me because the solution we're going to unpack today makes it possible. This right here, this is the core of the problem. We call it the AI dilemma. On one side, you've got this incredible push for innovation, which, let's face it, runs on data. But on the other side, you have the absolute necessity to protect people's privacy. For years, it's felt like a choice you have to make. You could have one or the other. But what if I told you that you don't have to choose anymore? In this explainer, we're going to show you exactly how new technology lets you have your cake and eat it too. Okay, so here's the game plan for today. First, we're going to dig a little deeper into that data dilemma. Then we'll unpack the first piece of the puzzle, a technology called confidential computing. After that, we'll look at the second piece, federated learning. Now, the real magic, and I mean the real magic, happens when we see how they combine into what's called confidential federated learning. We'll look at some real-world examples, and then we'll wrap it all up with a strategic playbook to help you figure out your next move. All right, let's dive right into our first section, AI's great data dilemma. This is really where the unstoppable force of AI innovation crashes right into the immovable object of data privacy regulations. And to really get the solution, we first need to pinpoint the exact weak spot in all our current security. Let's start with what we're already good at. Protecting data at rest. Data that's just sitting on a server's hard drive, that's a solved problem. We just encrypt it. If someone physically steals the disk, all they've got is a bunch of useless scrambled nonsense without the keys. So check, we got that one covered. And it's pretty much the same story for data in transit. Every time you see that little padlock in your web browser when you're banking online, that's TLS encryption. It's scrambling your data as it flies across the internet. So from your computer to the bank's server, it's protected. Another problem we've handled pretty well. But, and this is the big one, there is a huge gap. It's called data in use. You see, to actually do anything with data, to process it, to analyze it, to train an AI model on it, the computer has to decrypt it first. Just for a split second, that sensitive data sits in its raw, readable form inside the computer's memory, its RAM. And at that moment, it is totally exposed. A sophisticated hacker, a piece of malware, even a privileged admin at a cloud provider could potentially get a peek. This one vulnerability, this single Achilles heel, has been the biggest roadblock to unlocking the full power of AI for our most sensitive information. And that brings us right to section 2, and the first pillar of our solution, confidential computing. This technology was built for one reason and one reason only, to slam that door shut on the data in use vulnerability. It's designed to protect information during that most critical moment, while it's actually being processed. So the beating heart of confidential computing is a piece of hardware called a trusted execution environment, or a TEE for short. Now, the easiest way to think about a TEE is like a secure black box or a digital vault that's built directly into the computer's main processor. This isn't just another layer of security software. This is physically isolated on the silicon chip itself. Your code and your data go into this vault, they get processed securely inside, and only the results come out. Nobody, and I mean nobody, not the operating system, not the cloud provider, not even a rogue engineer with physical access to the server can see what's happening inside. So how does this magic vault actually work? Well, it's basically a simple 3-step dance. First, an application tells the processor, hey, create one of those secure enclaves for me, which is just a walled-off, protected piece of memory. Second, the sensitive data gets loaded into that enclave. And here's the critical part. It is only decrypted after it's safely inside those walls. And third, the processor's hardware itself acts as a bouncer, physically blocking any and all attempts from the outside to access what's inside. It doesn't matter who you are or what privileges you have on that machine, the hardware just says, nope, you can't come in. Now you might be thinking, okay, that sounds great, but how do I know that the digital vault I'm about to send my secret data to is the real deal and hasn't been tampered with? That is an excellent question, and the answer is a feature called remote attestation. Think of it as a trust but verify system. Before your app sends anything sensitive, it can challenge the TEE to prove who it is. The TEE then produces a cryptographic report signed by the chip manufacturer itself, like Intel or AMD, proving that it's a genuine TEE and it's running the exact code you expect it to run. It's a mathematical guarantee of trust. Now, like with anything in tech, there's more than one way to do it. The two main players in the market today are Intel and AMD. Intel's version is called SGX, and it's all about protecting specific little pieces of an application. AMD's version is called SEV, and it takes a much broader approach, protecting an entire virtual machine. This difference is a really important strategic choice, so let's break it down. The core difference here really comes down to precision versus convenience. Think of Intel's SGX like a surgeon's scalpel. It lets a developer be incredibly precise, wrapping just the most sensitive part of their code, maybe the part that handles encryption keys, inside a super secure enclave. It's powerful, but it can take more effort to implement. AMD's SEV, on the other hand, is more like a giant shield. It's designed to protect an entire virtual machine from a nosy cloud provider. It's less granular for sure, but it's often way easier to use for existing applications that you just want to lift and shift securely to the cloud. The right choice really just depends on your specific goal. Okay, so confidential computing is a game changer for protecting data when it's being processed in one place. But what if we could attack this problem from a completely different angle? What if we could just never move the data in the first place? That's where our second pillar, federated learning, comes into the picture. Federated learning, or FL, basically flips the entire traditional AI model on its head. For decades, the standard approach was get all your data, dump it into one giant data lake, and then bring your algorithm to the data to train it. Federated learning says, nope, we're not doing that. It does the exact opposite. It brings the algorithm to the data. The core idea is simple. The data stays put. Your sensitive patient records at a hospital, your customer's financial data at a bank, it never, ever leaves its home. So how does this actually work? Let's walk through it. Imagine a central server starts with a pretty basic, untrained AI model. It sends a copy of that model out to, say, a dozen different hospitals. Now, each hospital takes that model and trains it on its own private patient data, right there, on premise. And here's the magic trick. Instead of sending any of that patient data back, each hospital only sends back the mathematical updates, basically just the lessons the model learned. The central server then intelligently combines all those small lessons from all the different hospitals to create a new, much smarter global model. And the cycle just repeats, over and over. The model gets smarter and smarter, benefiting from everyone's data without anyone's data ever leaving home. But as you probably guessed, it's not quite perfect. Federated learning is a huge leap forward for privacy, but it has a catch. And this quote here really nails it. Just because the data stays local doesn't mean it's 100% protected. Researchers have actually shown that if you're clever, you might be able to analyze those mathematical updates and infer things about the original data. It's not easy, but it's possible. And that brings us to the real Achilles heel of standard federated learning, that central server. The whole system relies on the idea that this central aggregator is totally trustworthy and secure. But what if it's not? What if it gets hacked? Or what if a malicious insider at the company running the server decides to snoop on all those incoming model updates? That one single point of failure is a massive risk. And this is where it all comes together. Welcome to Section 4. This is the moment where our two heroes, confidential computing and federated learning, join forces. Each one is powerful, for sure, but each one also has a vulnerability. Now we're going to see how they combine to cover each other's weaknesses, creating a system that gives you real, verifiable end-to-end trust. This is confidential federated learning. The solution is just so elegant. You take that one weak spot in the federated learning chain, that central server, and you run the entire aggregation process inside a trusted execution environment, that secure hardware vault we talked about. So now, when the model updates arrive at the server, they go directly into that protected TEE. The aggregation happens inside the TEE. The new global model is built inside the TEE. The owner of the server, the cloud provider, literally everyone on the outside is completely blinded to the whole process. They can't see a thing. With one move, you completely eliminate that central point of failure. What you end up with is this incredibly robust, multi-layered defense. You get the hardware-based integrity from confidential computing, which proves the code is running securely. And then you can layer on top of that other cryptographic privacy tricks. It's like having a vault inside a fortress with armed guards. It's a defense-in-depth architecture that is just exceptionally hard for any attacker to break. Okay, enough theory. For Section 5, let's talk about where the rubber meets the road. How is confidential federated learning, CFL, actually being used to create real value in the real world, right now? The applications here are, frankly, mind-blowing. In healthcare, you can have hospitals all over the world working together to train a world-class AI model to spot rare cancers, and not a single patient record ever leaves the hospital's firewall. Think about finance. You could have competing banks securely pooling their insights, not their data, but their insights, to build a way more effective model for catching sophisticated criminals. For governments, CFL allows different agencies to analyze public health trends, say to track a pandemic, without creating some massive, scary centralized database of citizen information. And that brings us to our final section, your strategic playbook. Because, look, understanding the tech is step one. The next, and maybe more important step, is knowing how to position your organization to actually use it. And you need to know this market is moving at lightning speed. I mean, just look at the numbers. A projected compound annual growth rate of over 64%. That is just wild. You almost never see growth rates like that in enterprise tech. This isn't some slow, gradual change. This is a land rush. It tells you there is a massive, urgent demand from the market for solutions that deliver both AI innovation and real privacy. Waiting on the sidelines is just not an option. And we are not talking about a small niche market here. The projections put this at over $1 trillion within the next 10 years. $1 trillion, with a T. This isn't just a feature. This is quickly becoming the new default security layer for the entire next generation of cloud computing and AI. So where does this fit in with all the other privacy tech you hear about? Well, while other things like homomorphic encryption are amazing ideas, they have a massive performance penalty right now that makes them just too slow for training big AI models. Confidential computing, because it's accelerated in hardware, really hits the sweet spot. It gives you an incredible balance of strong, verifiable security and the high performance you actually need for real-world AI. This is the privacy tech you can deploy at scale today. So what should you do? What's your next move? Our analysis points to 3 really clear recommendations. First, for any serious, scalable AI project, you need to be prioritizing hardware-based tech like confidential computing. It's fast and it's ready. Second, think in layers. Use that remote attestation feature to verify everyone participating so you don't get bad data poisoning your model. And third, don't forget the data science. The best security in the world doesn't matter if your final AI model isn't accurate. You've got to invest in the advanced algorithms to make sure it learns properly. We started this whole journey with what seemed like an impossible question. How do you learn from data you can't see? We've now seen that confidential federated learning gives us a real, practical, production-ready answer. The tech barriers are falling, the hardware's in every major cloud, the software is maturing fast. The path is clear. And so the real question we're left with isn't about if this is possible anymore. The question is now about what. What impossible problems, what world-changing collaborations are you going to build now that you have the tools? The technology is here, the rest is up to you.